Hello and welcome to this video on reversible reactions. This is for the C8 module in AQA and it's mainly just aimed at GCSE really. So what I've drawn here is a blue powder and it being heated and it turning to a white powder. Now this is looking at hydrated CuSO4. You don't need to worry too much about what that means. It just means that water is locked in the crystal structure and it gives it this characteristic blue colour that you've probably seen in the labs back when we were all at school. And by heating it, you can turn that to anhydrous CuSO4, copper sulfate. And obviously you'll lose a few waters as well. Now, if I heat this up and I end up with the white powder, I can actually go back to my reactants just by adding some water. Obviously, mix them together and I will go back to the blue hydrated copper sulfate. And as a result, this reaction is said to be reversible. And we show that when we're writing our equations, rather than the single-headed arrow, we do this symbol here. There's two arrows over the top of each other, one arrowhead pointing in the forwards direction to the right, and one in the reverse direction to the left. And this symbol means that the reaction is reversible. And obviously there's a number of chemical reactions which have this symbol. And in a later video, I'll look at something called Le Chatelier's principle, which looks at the effects of influencing this reversible reaction. And there is one final thing we can kind of consider, which is the energy changes. So if I consider my hydrated copper sulfate here, when I heat this with a Bunsen burner, it's taking in energy. So maybe take a minute just to write down yourself two definitions for endothermic and exothermic. Maybe just pause the video and try that. Okay, so hopefully you pause the video. Endothermic simply means it's taking energy in from the surroundings. Exothermic means energy is being released. So if I'm accepting this heat from the Bunsen burner with my hydrated blue copper sulfate, then I'm taking in heat. And that means that it's I'm taking in that energy. That's an endothermic reaction. So if I draw a quick energy profile with energy on Y and reaction progress on X, an endothermic energy level diagram would look something like this, where my reactants are here, my products are up there. Obviously, delta H is going from reactants to the products, and my activation energy is going all the way up there to the peak of the curve. And this is the forward reaction. My reactants are down here, I add energy from the Bunsen burner, and I make my product P here. Now if I imagine taking a mirror image of this, then, just to give a very simple sketch, what I'd end up with, obviously I label that, is an exothermic diagram. So because my forward reaction is taking in heat from the Bunsen burner, taking in that energy, that's endo. But if I then go from products back to reactants, the mirror image there, then my reverse reaction is exothermic. And in these reversible reactions, you'll always find one direction is endothermic, it takes in energy, and the other direction, because of this mirror image of the energy level diagrams, I mean, this was originally our P in this scenario, and this our R, so we can see how in the forward reaction endo, reverse reaction exo, we've got these different energy changes. Now you could be asked in an exam to interpret observations, see that exo or endothermic, or maybe use some experimental data. Maybe they'd even give you a delta H value. So as well as the reversible reaction thing, you can definitely look up some examples of that. We've got this energetics consideration that one direction is endo and one is exo. So, hope you enjoyed the video, and we'll see you in the next one. Thanks very much.